Hello everyone, this is Dr. B. Mathura Bai, Associate Professor from the Department of IT, VNR, VJIT, discussing a topic on data structures by name AVL Trees. Proceeding further with the presentation, the agenda follows like this. We have introduction to the AVL tree, balance factors related to AVL tree, the rotations performed in AVL tree called single and double rotations, and the various operations performed in the AVL tree like creation, insertion, deletion, and finally the advantages and applications of AVL tree. Proceeding further, the introduction about AVL tree, it's a self-balancing binary search tree, where we have binary search tree is a tree in which every node will have a value which is greater when compared with the left child and it is less when compared with the right child. So the same property is applied here for the AVL tree, but it will have a special additional feature called as self-balancing. The name AVL stands for Adelson Welsky Landis, the authors who have found or invented this particular concept called AVL tree. The basic concept in AVL tree is the height difference between the left and right subtree is to be maintained with the help of a feature called balance factor. So in next slides we will see what is a balance factor. Now the reason for balancing this is it improves in searching efficiency. So we try to maintain a height difference which is less than or equal to 1. When we say the height difference between less than or equal to 1 means it can be -1, 0. So proceeding further, the need for AVL tree, the problems which we have identified with the normal binary search trees, when we perform insertions in the sorted binary search tree, it will form a skewed tree, something like a left skew or a right skewed tree, wherein the height is not balanced. So in order to reduce this, we go for AVL tree. The skewed balanced trees behaves like a linked list. Then the searching complexity will increase here. That is big O of n with respect to the binary search tree. This we are trying to reduce it to big O of log n with the help of AVL trees. So the solution for this problems of normal binary search trees and AVL tree, where it will automatically balances itself, maintains a height close to log 2 of n since we are balancing it, and the search, insertion, deletion operations, they become very efficient when we balance this particular binary search tree. Now if we see the node structure of the AVL tree, the AVL tree node consists of, just like binary search tree, a root node, a left child, and a right child. As we rightly said, the left child will possess a key value which is less than the root, and the right child will possess a key value which is greater than the root. Now coming to the properties of the AVL tree, since it is a binary search tree, it also possesses the same property of the binary search tree, that is it should be a binary tree with having either 0 or 1 or 2 children, and the left subtree values are smaller and the right subtree values of the root node are larger. And with respect to AVL tree, the special property is every node will have a balance factor which is of -1, 0 and +1. So if you can see, observe in this diagram here, we have every node has been associated with a balance factor which will be either 0 or +1 or -1 accordingly. So this property has to be satisfied by the AVL tree. Now in order to get these balance factors with this range of -1, 0 or +1, we do perform some rotations. So what are those rotations? We will see in next coming slides. Proceeding further, first we will see what is the balance factor. A balance factor is a metric which is used in self-balancing binary search trees to measure how balanced a node is. It determines if the tree rotations are needed or not based on the balance factor which is calculated. Now if we see the equation for the calculation of balance factor, it is the left subtree height minus a right subtree height. So for a balanced tree, that is for an AVL tree, every node should have a balance factor which should be -1, or in between the range, if we consider, it can have as a balance factor of 0 or 1. So that is how it has been put in an equation form like this. So if the balance factor becomes greater than +1, what does it indicate? It indicates it is left heavy. For example, in this AVL tree which we consider here, say for example, if I include one more node here, then it becomes a left heavy. So it is heavy onto the left subtree. left subtree side when compared to the right subtree. Similarly, if I include instead of this, if I include another node here on the right subtree, then it becomes right heavy. Now if I calculate the balance factor at that instant, I'll get a value less than -1. How we are getting, we will see in an example next. So this is how the example of a balance factor which we have considered here. So an example tree, if I consider a root node 30, the left subtree having 10, 20 and a right subtree having 40. So every node we have to calculate the balance factor. So starting from your node 10, the balance factor of node 10 is 0, since we don't have a left child and a right child. So 0 minus 0, 0. Similarly, the balance factor for the node 10, since we have a left subtree having node 10, a node called 10, and no right subtree, so we consider the height of this as 1. So 1 minus 0, 1. So this is how we calculate the balance factors for every node. Similarly, for node 40, if we check for the node 40, there is no left subtree, no right seed, so 0. Now coming to the balance factor of 30, if we check the balance factor of 30 here, the left subtree has got a height of 2 and a right subtree has got a height of 1. So 2 minus 1, 1. So this is how we calculate the balance factors. Now assume that in this case, if I have another node here onto the left subtree as node 5, satisfying the properties of binary search tree, then if we calculate, the balance factors will vary onto my left subtrees. So starting with your node 5, the balance factor will be 0. Starting with your node, next node 10, now the balance factor will be 1. It will change to 1 because left subtree has got 1 and right subtree 0. Now coming to the balance factor of 20, here I'll be having 2. This is left heavy. That is, left subtree is heavy when compared to the right, since there is no right subtree. Similarly, if I consider the 30 node, the balance factor will be, we have 3, height of the left subtree is 3, height of the right subtree is 1. So 3 minus 1, 2. So if we check the balance factors here of every node, we have got the nodes with a balance factor of 2 and 2, which doesn't fall in the range of the given specified values here, that is -1, 0, 1, which we treat this as an imbalanced tree. So for that balancing, we have to go for rotations. So proceeding further, so what are the different balance conditions which we consider for AVL tree? Are these are the conditions. The reason why we consider them is, if the balance factor is 0, it indicates that it is perfectly balanced. So if you check for this, the node 36 here, so I have a height of 2 on the left side, a height of 2. So this is perfectly balanced in the case of balanced tree. AVL tree. Now coming to the balance factor of +1, which indicates that the left subtree is taller by 1 height. So if we check for the node 20 here, so I have a left subtree height as 2 and a right subtree 1. So 2 minus 1, 1. So it's an indication that I am little bit taller by 1 position. So considering -1, right subtree is taller. So this is how we consider the AVL tree. The balance factors should have only these values. Proceeding further, now we have seen one example of an unbalanced AVL tree where we got a balance factor of 2. Similar to this example here. Now, since they doesn't fall in this range of -1 and 0 and +1, which means that we need to perform rotations to make it balancing, so that the balance factors will be within the range of -1, 0 and +1. So proceeding further. So how do we perform these rotations? So this is another example where we say that unbalanced thing is there in the rotation in the tree, for which the rotations has to be performed. So we'll see first the definition of rotation. So what do you mean by rotations? Rotations are designed to restore the balance in big O of 1 time, while ensuring the overall time complexity remains big O of log n. So in the AVL tree, we have 4 different cases. So to broadly categorize this, the type of rotations will be, we have single rotations followed by double rotations. Now in the single rotations, we perform only one rotation, that is either left or right. We call it as left rotation, right rotation. In the abbreviation notation, we represent it as LL, but doesn't mean that we are performing 2 left rotations. It is an indication that only single rotation of left rotation. Now coming to double rotations, since we have 2 rotations here, obviously the combinations will be left followed by right or right followed by left. So we will get a combination of left right rotations and RL, that is right left rotations. So proceeding further, single rotations of an AVL tree, example for left rotations. So we have considered one case wherein if you can see, it is a right skewed tree. If you observe the skewness, it is right skewed tree. And when we calculated the balance factors, we got the balance factors of 0, -1 and -2. So that's an indication that it is an imbalance. So in order to balance this, where we have a pattern of the form of skewed, we go for single rotation. Since it is a right skew, we perform a left rotation, wherein we make node 10 as a left child for node 20, satisfying the property of binary search tree property. So which is shown in the next diagram here. Now after that, if we calculate the balance factors, they all remained balanced here. So this is how the imbalancing is being balanced by performing a rotation called left rotation. That is a single rotation. This is applicable only for the pattern where we have a right skewed. Similarly, proceeding further with another single rotation, that is a right rotation, wherein if we have a pattern of a AVL tree or a binary search tree pattern, wherein we have a left skewed. Since it is a left skewed, we have to perform a right rotation. Only skewed patterns will have single rotations. Depending upon the type of skew, we will perform the opposite rotation. If it is a left rotation, we perform right rotation. If it is a left skewed, we perform right rotation. If it is right skewed, we perform left rotation. Just now, as we have seen in the previous slide. Since it is right skewed, we perform left rotation. Now it is a left skewed, we'll perform right rotation. So when we consider this particular example here, we have a balance factor of 2, which is an imbalance, for which we will perform a right rotation, a single rotation right, where we make 30 as a right child for node 20, maintaining the property of a binary search tree, thus balancing the factors. The balance factors will have within the range of -1, 0 and 1. So this is how the single rotations are performed on the AVL tree. Now proceeding further for the double rotations. In the double rotations, if at all we have a pattern something like other than this skewed, something like this pattern, where we apply the double rotations. And for this particular example here, if we consider the balance factors for each node, we have 0, 1 and 2, which is an imbalance. For this, we have to perform a double rotation. The reason why we can't perform a single rotation here is the pattern is not skewed. So we have to go for double rotation. Now, when we apply double rotation, if we just split it in terms of left followed by right rotation, the split would be something like this, where maintaining the property of the binary search tree, your 10 node will be made as a left child for node 10. Thus, the balancing factors again are recalculated where they are still imbalanced. The reason is, so we have done only one rotation here. Now, followed by this, we will perform a right rotation, wherein the tree will be now balanced with the balance factors as 0. So this is how we have a combination of left followed by right, which we put together as a LR combination, that is left-right rotation combination. So in the AVL trees, if we can obtain any patterns of this form, we can directly put it, instead of splitting as separately single rotations, we can combine them together as a double rotation as left-right rotations. Proceeding further with the next double rotation, that is a right-left rotation. Now, in the right-left rotation, if we can observe a pattern like this is not a skewed pattern, so we cannot apply a single rotation. We have to go for double rotation. Now, when we apply the double rotations, as per the binary search tree property, so your node 30 will be made as a right child for 30. So, where we will have the right rotation, followed by this a left rotation. So, combining these two together, we call it as a right-left rotation, where finally the tree will be balanced. Okay. So, proceeding further with the operations of the AVL tree. The very first operation which we perform on the AVL tree is creation. The steps to create an AVL tree is, we start with an empty tree. Insert the nodes into the tree, just like the binary search tree node insertions. But after insertion of a node, we calculate a balance factor for every node, where the balance factor of a node is calculated as the height of left subtree minus height of the right subtree. Now, after we calculate the factors, we check for the imbalance. So, what can be the balance factor where we will get this imbalances, which is less than -1 and which is greater than -1, which means that if a balance factor is -1, 0, 1, then we consider it to be balanced. Other than these three values, if we get any other values, then obviously we'll consider it as unbalanced. So after checking for the imbalance, then we go for balancing it, for which we apply rotations, the appropriate rotations based upon the pattern which we identify. As just rightly said, if we have a skewed patterns, we apply single rotations. If we have the other patterns combination, we go for double rotations. Okay, proceed. And this process is repeated until every node satisfies the AVL balance conditions, that is -1, 0 and 1. So if we can take one example for this, after creation, insertion operation, the insertion is done based on the binary search tree property, wherein the keys of the left child will be less when compared to the keys of the root, and the rights will be greater than that. The reason for this conservation of these AVL trees is, as we rightly said, the insertion operation will be big O of log n, since we are balancing it. Okay, so this is an example of an already created balanced tree for which we have inserting a node 10. So after insertion of the node 10, after insertion, as per the binary search tree property, the node 10 will be a left child for node 20, wherein the balanced factors calculated after insertion will be like this. So which indicates that it is a balanced tree. Now I assume that in this case, if I insert one more node called 5, where that 5 will be after insertion as a left child for node 10 based on the property of binary search tree. Now if we recalculate this, this will be 0, this was considered as 1, and this will be 2, and this will be 3 minus 1, that is 2, where now we got a pattern of imbalance. Now observing the pattern of imbalance, the imbalanced nodes are said to be node 20 and node 30, where the balance factor is 2 and 2. Now if we see the pattern of this, the pattern of this is something like skewed. It is left skewed, which means that I have to perform a right rotation. So after I perform a simple right rotation here, now 20 will be considered as a root, 30 will be the next node, right to it, 40, followed by it 10 as the left child and 5 as the left child. So this is how the rotations are performed after single rotation, that is right rotation. Now if we calculate the balance factors, this is 0, this will be 1, this is 2 minus 2, that is 0, this will be 0 minus 1, so minus 1, this is 0. So it is satisfying the property of balance factors, that is ranging from -1, 0 and 1. So that is how the insertion operations are performed. So after inserting of the node, check for the balance. If it is balanced, perfect. If it is unbalanced, then perform the rotations as per the choice. Proceeding further, the next operation, that is deletion. Now, how do we perform deletions? The deletions of AVL tree is same like your binary search tree deletion, where we have 3 different cases. The first case would be a node with no children, where we simply delete it from the binary search tree. The other case would be where we have a node with one child, either left child or a right child. So if we have only one child, just swap it with that child and then perform the deletion operation. The third case, where we have a node with 2 children, where we will consider the in order predecessor or an in order successor. Accordingly, we will swap and then we will delete the node. The same rules applied for the deletion operation in AVL tree. The purpose of going for this is we have a time complexity of big O of log n, which is always a balanced fund. Okay, so proceeding further, the deletion operation here. For example, in this case, in this example, if you consider we are trying to delete a node 30. This falls under a category of a node with 2 children. There are 2 children for that particular node. So when we have 2 children, then you have to consider either the in order predecessor or the in order successor. If I consider the in order predecessor, then I have to consider the left subtree. In the left subtree, you have to swap it with the maximum element in that left subtree. So here I have only 25. In case if I have some other nodes followed by it, then in that case I have to consider the minimum element in the left subtree. That is said to be an in order predecessor. Now if I try to replace it with a right subtree element, then I have to consider in order successor, where the successor value for the right subtree will be the maximum element. A minimum element for the right subtree, maximum element in the left subtree. So here we have just taken an example of considering node 25. So just swap it with node 25. So 30 is being deleted here by replacing. Or else we can have either swap with 40 as well. Okay, so proceeding further, these are the time complexities of the operations. For all the operations like search, insert, delete, in the binary search tree worst case, we have big O of n, because we are considering the height, which is unbalanced. Whereas when we go for the AVL tree, since it is balanced, always we get big O of log n. This can be an advantage when compared to the binary search tree. So finally, the advantages of AVL tree can be, since it is a self-balancing tree, it can be applied for the operations where the search, insert, deletion operations are mostly used. In that notations, we can use it. So when compared with your binary search tree, preferably we'll go for AVL tree. Now coming to the disadvantages of the AVL tree, when we compare with the red-black trees and everything, we have to perform rotations here, where rotations will be taking more time. So the computations are more when compared with your other trees, that is red-black trees. This is said to be one of the limitation of or a disadvantage of AVL tree. Finally, the applications. AVL trees, we can use it for different notations. We can use it in a compiler design for representing the parse trees. We can also use it for your notations, representations of the hash tables. So in your hashing concept, if you want to represent a dictionary, you can use AVL tree. So there are so many examples for this. So thank you for this opportunity. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.